So hopefully you remember from yesterday, we were talking about taking a function, taking a curve, and sketching a bunch of rectangles underneath it and approximating the area underneath that curve, right? And then we said, well, the way to get this to be a more accurate representation of the actual area would be to make the number of subintervals, or the number of rectangles that we draw, approach infinity. And so we said, well, let's make the limit as n approaches infinity, where n is the number of subintervals, right? N subintervals, or n rectangles, of the sum from the first rectangle, k equals 1 being the first rectangle, to the nth rectangle, of the heights of each of the rectangles times the width of each of the rectangles. Everybody basically remember that from the other day? That's what we were doing. That's what we had. We developed this limit with this summation inside of it that was supposed to give us an exact value of the area underneath the curve. Everybody good there or no?
So I'm kind of confused on what K represents, because I know N is the number of rectangles.
Right, n is the number of subintervals, or the number of rectangles. The K is just any rectangle or subinterval that we choose on our interval. So we start at k equals 1 being the first rectangle, and we go up to n, which is however many we have. So k just represents any arbitrarily chosen random subinterval or random rectangle on our interval. Okay, it's just a generic representation of a rectangle, or of a subinterval. Does that make sense?
Yeah.
Okay, so yeah, when we talk about the kth rectangle, it's just some rectangle within there. It could be the first one, it could be the second one, it could be the 100th one, it could be any of them. We need, so what we do is we write a formula in terms of k that is generic for any rectangle and is true for any rectangle within there. Does that make more sense?
Yeah, thanks.
Yeah, no problem. So the C sub k is, we were talking about midpoints, but it doesn't have to be midpoints. We could be, it could be the right-hand endpoint, it could be the left-hand endpoint, it could be any point within that subinterval that we're looking. And in fact, what we're mostly going to actually use is the right endpoints of them, because it makes the arithmetic a lot easier. And then delta x, like we said, was the width of each subinterval, and the subintervals are all going to have the same width now, because we denoted that they would be. We made our subintervals equal length. So each one is equal to the length of the interval, b minus a, right, where b is the endpoint and a is the starting point, divided by the number of them, which is n. So we'll note that delta x is always equal to b minus a over n. And we're going to need to use that fact as we move on later today. Everybody so far good? Sort of recollecting what we talked about yesterday? I hope. Okay. So this notation is a little bit of a pain, right? First of all, it's still got a function f of c sub k, it's got the ends, it's got the limit, it's got the summation, it's got a delta x, it's got a bunch of junk in there that's kind of irritating. This was the notation that Newton used as he was developing calculus. At the same time Newton was developing calculus, there's another guy who was also working on it. His name was Leibniz. And Leibniz said, well, all this notation is great, let's find some shortcuts and use this other notation that I'm going to come up with. And he drew this thing called an integral sign, which basically just looks like a stretched out S, and that's called an integral sign. And he said, if we have on some interval from A to B, this limit that we were just dealing with, I'm going to just abbreviate that basically as an integral from A to B of f of x dx. And you should recognize a dx, right? What does a dx represent when we were talking about our differentials with derivatives? It's just a very small change in x, right? And that's exactly what this delta x is, right? The delta x is the width of each subinterval. And as n goes towards infinity, those widths become infinitesimally small, right? And so that's what the dx, it's the infinitesimally small width of each of those rectangles. And then f of x is just the height of your function. So effectively what this is doing is saying, This integral sign is saying, all right, we're doing this limit as n approaches infinity of the sum from k equals 1 to n. That's the integral sign. That's all that stuff of our function times the width of the rectangles. Okay. And so we call the bottom number the a number the lower limit. We call the higher number the upper limit. That's the integral sign, and everything inside of it we call the integrand. And so we want to get used to this notation. And what we need to first be able to do before we can come up with some tricks about how to do these integrals easily is we need to learn how to convert back and forth between the two different forms, because the AP test is going to ask you at least once or twice to convert back and forth. Generally, they want you to go from this notation, the nice easy Leibniz notation, into Newton's annoying limit summation notation, but sometimes they want you to go the other way. So that's what we're going to work on now, is converting back and forth between them and trying to evaluate if we can. Everybody good with that in this new notation or no?
I have a question.
Yeah.
For Newton's notation, you don't actually put a in the interval of a to b on like the actual equation, right? Do you just mention it somewhere else?
Yeah, it'll be written out with the problem. We'll say, hey, we're looking at the interval from -2 to 11. We want to find the area underneath the curve. And so then you would say, all right, well, it's all of this. And then you use the a and the b in your delta x, because remember your delta x is always equal to b minus a over n. If you were trying to evaluate it, you plug those numbers in as delta x. Does that make sense?
Yeah, thanks.
Yeah, I think it'll make more sense as we move forward too. You'll see on the next page how we go from this notation and where this lies and turning it into this notation. So let's do that real quick. So what we've got is an interval from -1 to 3 that we've partitioned into n subintervals of equal length. We've got m sub k as the midpoint of the kth subinterval, remembering that the kth subinterval is just some arbitrarily chosen subinterval. And we want to express this limit as an integral. So it's got everything we need, right? The limit is n approaches infinity of the sum from k equals 1 to n. That piece of it is just our integral sign. And what should the lower limit of our integral be?
-1.
Should be -1, right? That comes from right up here. And the upper limit should be 3. And then our 3 m sub k squared minus 2 m sub k plus 5, well, that just represents the height of our function at m sub k. And so the height of our function is just the value of the function. That should let these m sub k's just turn into x's for our function. 3x squared minus 2x plus 5, right? Because we're looking at f of x. And then lastly, this delta x should turn into dx. And that's all you have to do to convert from Newton's notation into Leibniz's notation. Good or no?
Good.
All right, I think that's usually pretty straightforward. The harder part is going from this notation into Newton's notation and then being able to successfully evaluate the summation and the limit. So that's what we're going to try and do right now. Hopefully we'll have time to do 2 of these. We may only have time to do 1 of them, but we're going to at least try to do 1. So we're going to look at the integral from 0 to 2 of 3x dx. So first off, what's this question asking? What is the answer to this integral represent? Remember, what is an integral? An integral is just the limit as n approaches infinity of that summation. And what is that limit of that summation doing? What is it representing?
The area under the what?
the area underneath the curve. Right now, this isn't a curve per se, it's a straight line, but it's the area underneath the curve. And we call any function a curve. So all this integral is saying is what's the area between this curve and the x-axis from 0 to 2. So first off, does this actually require any calculus?
Nope.
No, we should be able to do this. I mean, you should have been able to do this when you were in like 4th grade, right? This is just a triangle, isn't it? What's the base of the triangle?
2.
Base of the triangle here is 2. And what's the height of the triangle up here?
6.
6. Our area should be 1/2 base times height, or it should just be 6, right? So we know that this integral should equal 6. So what we're going to do is we're going to try to turn it into the limit with the summation and try to evaluate it and hope that it comes out to be 6. Now this one's a fairly easy one because it's just a linear function. And we'll note that there's an easy way using geometry to do it. But for most other ones, you know, if I put in x cubed plus 5x minus 7 from -2 to 10, well, that's not something you're easily just going to be able to use geometric formulas for, right? You're going to have to actually be able to do the calculus for it. We'll start with the easy ones where we know what the answer should be so we can check our work. So first off, this integral should always turn into something that starts out as a limit as n approaches infinity of a sum from k equals 1 to n of f of x sub k. So what is f of x sub k? What's f of x?
3x.
3x. And so f of x sub k ought to just be 3 x sub k. And then times delta x. Everybody good with that so far? That's just straight up converting into that notation that we were given at the beginning. All right. Cool. So then what is delta x? Well, we said delta x is always equal to b minus a over n, which in this case is, what's b?
2.
And a is 0. So delta x is just 2 over n. So we're going to be able to replace the delta x with 2 over n in just a second. We also need to figure out what is x sub k, right? And x sub k is just how far over we've gone from a in the kth subinterval, so in any arbitrary subinterval, to go up 3 times that to find the height of the rectangle. So what I'm going to do is I'm going to draw some rectangles in here, pretend those are all the same width, and pretend that I've drawn an infinite number of them. And I've done them all from right endpoints. Everybody good with that?
Yeah.
Okay. So let's first figure out what is x sub 1. X sub 1 is just how far over I go from x equals 0 before I go up to find the height of that first rectangle. So how far over do I go? What is the width from 0 to this value x sub 1 right there?
2 over n.
Yeah, I just went over the width of one of those rectangles, right? I went over delta x, which is 2 over n. All right, well, what about x sub 2? How far over from 0 did I go to get to the next one, x sub 2? I went over 2 over n once, and then I went over 2 over n a second time, didn't I? Do you guys agree with that?
Yeah.
That's the height of the second one, or that's the how far over I've gone, is where I plug this x value, x sub 2, into my function to get the height 3 times it. Well, what about the third one? What have I done? I've gone over 2 over n for the first one, 2 over n for the second one, and another 2 over n for the third one. So that ought to be 2 over n times 3. With any luck, you're seeing a pattern here, right? X sub 4 ought to be 2 over n times 4. X sub 5 ought to be 2 over n times 5. So for any arbitrarily chosen subinterval, x sub k, how far have I gone over? I've gone over 2 over n times k. Everybody okay with that? Haha, okay. Any issues or questions there?
No.
Okay. So now we can go in and replace our x sub k with 2k over n and our delta x with 2 over n and get a new limit and a new summation. So we have the limit as n approaches infinity of the sum from k equals 1 to n of 3 times x sub k, which was 2k over n, times delta x, which was 2 over n. And now we'll see that we're down to just 2 different letters in there, right? We've just got k and n. We've gotten rid of all the x's, which is nice. And we should be able to multiply all those things together, which gives us what? 12k over n squared, it looks like. And generally, either one of these 2 steps is as far as they will ask you to go on the AP test. They won't actually ask you to evaluate it. I forgot my summation. They won't actually ask you to evaluate out the limit and the summation usually, but every once in a while they do. So I think it's important that we know how to do it. So let's go on to the next page and see if we can evaluate out that limit and that summation. So we've got the limit if n approaches infinity of the sum from k equals 1 to n of, what was it, 12k over n squared? Everybody good with getting to that point?
Yes.
Okay. So for just a second, we're going to ignore this limit. We're going to bring it back in a second. For just a second, we're going to ignore it. We have 2 different letters inside of this summation. True? We have k and we have n. One of those letters is a variable, and one of those letters within this summation is a constant. So which one is the one that is changing? Which one is the variable and which one is the constant? Any ideas?
K is the constant.
Nope. K is the variable, right? Because if you think back to what we were doing yesterday with the summations, K is changing from 1 to 2 to 3 to 4, all the way until it gets to some number n, right? And that number n, which in this case just represents the number of subintervals, is a constant. That n could be 7, or it could be 1,000, or it could be 1,000,000. It's however many subintervals we have. And if we're not sitting here looking at a limit as n approaches infinity, then that n, we know, is just some number. And then so within the summation itself, n is constant. N is however many subintervals I have. Okay. K is changing. K is going from the first to the second to the third rectangle. Does that make sense to everybody? Or no?
Yes.
Okay. So we do still have our limit though. So we'll put that there. And whenever you have a summation with a constant inside of it, you can pull that constant out of the summation and just multiply it by the rest of it at the end. So 12 also is a constant, right? So we have 12 over n squared as a constant. And then times the sum from k equals 1 to n of just k. And with any luck yesterday, you remember what the sum from k equals 1 to n of k was. We figured out what that was, right? That was like adding 1 plus 2 plus 3 plus 4 all the way up to n. And what did this summation right here, this piece of it, what did that equal?
Isn't it like n plus 1 times n over like 2?
Yeah, it is not just like that, but it is exactly that. And now we've gotten rid of all the x's a few steps ago. Now we've gotten rid of all the k's. We're just down to a limit as n approaches infinity of some function that's all in terms of n, which we can then simplify down. This is now a limit as n approaches infinity of 12n squared plus 12n over 2n squared. And hopefully you recognize a couple of things. One, that this is a limit as n approaches infinity, which is effectively just asking what's the horizontal asymptote to the right of this function, which you should be able to just figure out really quickly. Since the degree of the numerator is the same as the degree of the denominator, and it's a rational function, you just divide the leading coefficients, you should get 6. Or if you don't recognize that right away, you can use L'Hopital's rule if you wish. Or you can divide everything by n squared also if you want to do that, that being the highest term. But using L'Hopital's rule, this becomes a limit as n approaches infinity of 24n plus 12 over 4n, which is still infinity over infinity. And so we could use L'Hopital's rule again to get a limit as n approaches infinity of 24 over 4. And the limit of a constant is just a constant. And we get 6, which is what we thought that it should be from what we were doing earlier with the geometry. So we successfully evaluated this. Any questions on that?